So I want to actually talk about four separate pieces of evidence for inflation, the first of which is the large-scale uniformity of the universe. The cosmic background radiation is our strongest evidence for this uniformity, and astronomers have now made very careful measurements of the uniformity of the cosmic background radiation, and have found that it's uniform to 1 part in 100,000, which I think is really amazing. One way of perhaps getting some handle on how uniform by 1 part in 100,000, what it actually means, is to imagine, for example, trying to construct a marble that's round to an accuracy of 1 part in 100,000. And you can calculate how precisely the surface of the marble has to be constrained, and it turns out to be on something on the order of a wavelength of light. So modern technology knows how to do that. We build lenses that are accurate to a fraction of the wavelength of light. But it would really mean that the marble would have to be round to the accuracy of a high-quality lens in order to be this round. But the universe we just find this way. We don't have to do any special grinding. And somehow the universe got to be this incredibly uniform state without our knowing how it happened. So the other important point in trying to understand what this means is to know something about the history of the cosmic background radiation. It says here that the cosmic background radiation was released when the universe was about 380,000 years old. By released, what's meant is that prior to this time, the universe was so hot that everything was a plasma. And in a plasma, photons are constantly being scattered off of the free electrons in the plasma. So even though each photon is instantaneously moving at the speed of light, as photons do, the photons are constantly being rescattered into different directions. And the net result is that during the early period, before 380,000 years, the photons essentially went nowhere. They were just basically glued to the hot matter, to the plasma. Then at 380,000 years, the universe cooled enough so that the matter neutralized, and suddenly we had a neutral gas like the air in this room. And neutral gases are highly transparent to photons. And it's a little dangerous to just imagine directly extrapolating from the room to the universe. But in this case, it works. You can go through the mathematics. The universe really is transparent to photons since the time of recombination, since the time when the universe became neutral. So the result of that is that the photons that we see today in the cosmic background radiation really have been traveling on straight lines since 380,000 years after the Big Bang. And the implication of that is that it gives us an image of what the universe looked like at 380,000 years, just as the photons traveling from my face to your eyes let you know what my face looks like. It's as simple as that. So what this means is that the universe itself was incredibly uniform to 1 part in 100,000 accuracy by 380,000 years after the Big Bang. So that now gives us a well-defined challenge. Can we explain how the universe got to be so uniform by this time? Now, I should add that you could always just assume that the universe started out completely uniform. We don't really have a theory of how the universe actually started out. So if you want to make that assumption, that's fine. But it seems to be a very bold assumption. If, on the other hand, you'd like to be able to describe how the universe became uniform through physical processes that we understand, then we're forced to address this question. And that's the context in which inflation gives a very nice answer. In the context of conventional cosmology, without inflation, you can do a pretty simple calculation to trace these photons back to where they came from. So you can imagine looking at a photon coming from that direction in the sky and another photon coming from that direction in the sky and trace them back. And what you find is that when those photons were emitted, they were separated from each other by about 100 times the distance that light could have traveled up until that time. So that indicates that if you believe that nothing travels faster than light, and as far as we know that's true, there's no way that that photon could have known anything about what was happening to that photon at the time when these photons were emitted. Yet somehow that photon and that photon knew how to be at the same temperature at the same time to an accuracy of 1 part in 100,000. So that's the issue, sometimes called the horizon problem. And within the context of the conventional Big Bang theory, there's no way to solve that. However, inflation provides a very nice solution. In inflationary models, we're inserting into the scenario of the universe this period of incredibly rapid exponential expansion. And that means that if we imagine taking the visible universe today and tracing it backwards in time, when we come to the period of inflation, it suddenly becomes rapidly much smaller because we're doing the inverse of the expansion. So before the inflation started, the region was vastly smaller than anybody would have thought in the context of conventional cosmology. So before the inflation, there's plenty of time for this tiny region to become uniform in both density and temperature, in the same way that the air in this room spreads itself out to an approximately uniform temperature and approximately uniform density. That's basically what thermal equilibrium is about. And then, once this uniformity is established on this tiny scale, inflation takes over and magnifies this tiny speck to become big enough to include everything that we see today, giving us a very simple explanation for why everything that we see today, including the cosmic background radiation, is incredibly uniform.